today I'm going to tell you a little bit about our HPC Toolkit performance tools and hopefully give you a sense of how you can use them to understand your application's behavior and hopefully improve its performance. So before I get started, I just wanted to give a couple of brief acknowledgments. So a lot of this work of late has been funded from the DOE Office of Science through the an award called PIPER, which stands for Performance Insights for Programmers in Exascale Runtimes. Also, we have a subcontract with Argonne, one from Livermore, and some gift money from Intel. This isn't all just my own work. I have a team of people, so there's several research staff, and then some of my former students are listed as well. So the challenge for you as computational scientists is that the platforms are rapidly evolving and the applications are becoming more sophisticated over time. So the architecture, well, there's been rapid changes in the multi-core microprocessor design. So we've gone from just having a few cores back in a decade ago, and now we're heading to 70 cores and 4 times as many threads. There's increasing architectural diversity, so we have leadership computing facilities that have multi-core processors. The emerging ones will have these many-core processors with as many as 72 cores. Accelerators on some of the systems, so you have both a multi-core processor equipped with a GPU, and there's increasing parallelism within the nodes. Then on the application side, it turns out that you have to adapt your applications in order to deal with the fact that the architectures are changing. And so you need to exploit thread-level parallelism in addition to using MPI. And so with the newest generation of architectures, using an MPI everywhere design doesn't work out so well because there isn't enough memory. And actually, to get the benefit of all of the hardware threads, it's best to use them in kind of a shared memory mode. So I understand that you've had some introduction to OpenMP, and so mixing both MPI and OpenMP, you get the scaling for the large machine with MPI, and then you can use OpenMP within the nodes for this hybrid parallelism. So getting good performance, it's not just about getting the cores active, also it's about exploiting the vector performance within the cores. And then while you're trying to add threading and improve the vector performance, I assume that most of you are also working on new science problems as well. And so your codes are changing in many ways. You're changing to add science to them, and you're also changing, trying to take advantage of the latest generation platforms. So in order to help you adapt the codes for the changing architectures and improve the scalability both within and across the nodes of these parallel systems, and then also to help you understand what the weaknesses are in your algorithms, that they don't have the scaling properties that you were looking for, or they don't have the locality that will deliver performance, that you can use performance tools to get some insight into what are the principal weaknesses of your application, and then you can use this to prioritize your development and decide where you can best invest your efforts to improve the scalability and performance of your code overall on these large-scale systems. So some of the challenges that you face, well, on today's systems, you have multi-level parallelism. So you have multiple cores within a node. You've got instruction-level parallelism within the cores. You've got short vectors. And on some systems, you have offloaded computation to accelerators as well. There's a multi-level memory hierarchy. So how many people know what a cache is? You talked about cache? Okay, so you understand the memory hierarchy a bit, and that the caches that are close to the processor run at the regular clock rate, and the ones that are further away, it takes several cycles to actually to get the data out of them. So you have to deal with the fact that you've got these multiple levels of parallelism and the multiple levels of cache, and that as a result, the gap between typical performance and peak performance is huge. And so on an untuned code, you might get 5% of peak, and if you work really hard, you might get 20% of peak, and the heroes who get Gordon Bell Prizes get like 50% of peak. And so, it's an arduous task to try and get the most out of these systems. So the applications are often rather complex themselves. I don't know what you're working with, but the things that I've worked with in my experience, They have frameworks with all sorts of moving parts that are plugged in. And so these are challenges just to measure and analyze the data from the code. And then to understand what their behaviors are and provide some advice on how to tune performance can be rather difficult. And then doing this on supercomputers is actually even harder because on the case of the Blue Gene systems, there's a microkernel-based operating system, and so it's not just standard Linux, and so the tools have to cope with the fact that we've got kind of a unique environment, and you're not concerned with just the processor performance, it's the data movement, the communication, and the I/O. And so what we ideally should have are some tools that give you insight into all these capabilities. So I would argue that what users want is they want some programming model independent tools, whether you're using OpenMP or whether you're using MPI or whether you're using them both or whether you're using Charm++. The tools should work with anything. They should work on any of the platforms that you have available to you, whether it be the Titan system at Oak Ridge or the Mira system here. You'd like to have accurate measurement of your complex codes. And so many codes are multilingual. You might have some kernels that are written in Fortran, some other pieces that are written in C++. There's parallelism within and across the nodes, MPI parallelism across the nodes, and maybe OpenMP or accelerated computing going on inside the nodes. Highly optimized code, so you've got optimized loop nests, instantiated C++ templates, inline functions. You've got binary-only libraries for maybe some of the components like the runtime library for OpenMP or some math libraries. And so that's the environment that we have to deal with. So we need to take these complex pieces of software running in a complex execution environment and be able to measure and analyze what's going on. And based on those measurements, what we'd like is some insight into what's going on in your application. So we'd like to be able to pinpoint the bottlenecks in your application and explain the problems, and then have all of these tools scale to the petascale and beyond. So let me tell you about HPC Toolkit, and then I'll tell you how we use it to pinpoint scalability bottlenecks, and I'll show you a demo. And then I'll show you how we can use it to understand the temporal behavior of your application over time, also using a demo, how to assess the variability among processes or threads, how to understand threading performance, and then some of the things that we're working on. So HPC Toolkit employs binary level measurement and analysis. So we're not instrumenting your source code or anything like that. We're collecting measurements about your machine code, observing fully optimized machine code, and it supports multilingual codes for that reason. We typically avoid instrumentation, so the only instrumentation we have are really kind of to catch thread creation and exit and process creation and things like that. In general, we're measuring using sampling. So we have an event trigger that's periodically interrupting your program as it runs instructions or consumes time. And so by choosing an appropriate sampling frequency, you can control the overhead. So if the overhead's too high, then you turn the sampling frequency down. So we can collect data for large-scale parallelism over long periods of time because using the sampling is relatively lightweight, and we can also just collect it into profiles that don't grow much in size depending upon the execution time in your program. Then we correlate multiple and derive performance metrics. So often understanding the application performance requires knowing more than one thing. Instead of just knowing time, you might need to know, well, how many instructions we're executing and how many loads and stores and how many of those instructions were vector instructions, those sorts of things. And so we can collect all that information and then compute some derived metrics, and I'll show you how to do that. And then you associate these metrics with both static and dynamic context. And when I say static context, I mean things like procedures and files and loop nests. And by dynamic context, I mean dynamic call chains. And so it's important to know if I'm spending time in MPI wait, how did I get here? And then finally, since we're collecting data for a massive system, what we want to be able to do is to support top-down performance analysis. So rather than worrying about all of the data you have, let's figure out what's important and then how to find the results that are of interest. So our workflow is rather simple. We've got a couple of pieces, and so you compile your source code and create an optimized binary using the normal mechanisms, so your compilation and link step with your make files. So for dynamically linked binaries on Linux, you don't have to do anything. You can just use the make files that you've got, and then you launch with our tool. For statically linked executables, such as on BlueGeneQ, All you need to do is add this HPC link tool. In your final link step, you add HPC link as a prefix, and then what that will do is, as your application gets linked by your makefile, it will inject our monitoring code into your application, and it'll become part of your application itself. And then when you launch the application, you get to specify how to turn on the tool using some environment variables. Actually, I think that's on the next slide. And so for the statically linked execution, then it uses linker wrapping to catch control operations like process and thread creation, finalization, signals, things like that. So then to profile, you can, on like a Linux cluster, you can use this HPC run utility. So when you launch a dynamically linked application, instead of saying MPI run, you might say MPI run HPC run your application. And what that will do is just turn on the monitoring for each of the node programs in your application. And for a statically linked one, then you use some environment variables. So when you submit it with the job launcher, you set some environment variables saying what kinds of things you want to monitor. And then the tool will take care of the rest. What it'll do is it'll collect statistical call path profiles for events of interest. So what do I mean by a call path profile? What happens is we're setting up either hardware counters to overflow with a particular threshold, or we're setting up a timer to interrupt your program periodically. And then every time we get one of these interrupts, we'll note that I'm at a particular instruction in the program. I'm at some instruction in routine C when called from B, when called from A, when called from main. And so we find out where you were, and we find out the context that you were in. And then over time, as your application runs, we accumulate this set of contexts into a tree. So conceptually, you can think of maybe main as being up at the top, and maybe this subtree represents a initialization phase, and maybe this represents a solve phase, and maybe this represents a post-processing phase. Okay, so what we're doing is we're collecting all of these samples over time, and we fit them into this tree. And the important thing is that the overhead of collecting this information is proportional to the sampling frequency, not the frequency with which you're making calls in your application. So by turning down the sampling frequency, in fact, you can control the overhead of your measurement. So then the next thing we do is we do some binary analysis. So we analyze your application binary. We have a utility called HPC struct. What it does is it recovers the program structure. So it analyzes the machine code, the line map, the debugging information that's present in the executable. It identifies where the loop nests are, where there's inline code, and then it maps all of the machine instructions back to the original source code. So what we do with that, then, so we've profiled our execution, and we get this call path profile that tells us where all the time was spent, or where all of the resources were consumed, whatnot. And then we do this binary analysis to collect this program structure that says, well, how does the machine code relate back to my application source? And then we have another utility called HPC prof that will take the structure information and the dynamic measurements and knit them together and put it together to something that you can understand. So you can use this utility to take information from multiple threads, multiple processes, multiple executions, and it will correlate these metrics with the static and dynamic program structure that we've extracted using this binary analysis. And then finally, we have some presentation tools. So there's one called HPC Viewer, which shows you a source code-oriented view. And there's another one called HPC Trace Viewer, which shows you an execution view over time. What it allows you to do is explore the performance data from multiple perspectives. So you can rank order by metrics to say, well, what's most important to me, and then where am I consuming this metric? You can compute derived metrics like scalability, loss, or waste to guide your analysis. You can graph these metrics over all of the threads or the processes to see who's consuming how much. And then you can see how these things evolve over time. So here's our code-centric user interface. And you probably can't read it from where you are, but I want to just point out a couple of things. So we have a source pane up at the top, and we have a navigation pane. And so this typically is showing, say, calling context. So this is showing an indented call chain. And then we have some metrics over here. And so what this is doing is it's showing like a summary view for an entire parallel execution. So if you had MPI threading, what we're showing is sort of a unified view across all of the threads it's like the sum of all of the activity across all of the threads. And if you're using MPI plus OpenMP, it's like the sum of the activity over all the nodes. Where did I spend my time? Where was their inefficiency losses? So this is the source code-oriented view. And so there are a couple of different ways that you can use this. So there's some view controls, so I can look at top-down, where I can see from main and all of the things it calls where my time was spent. And then I can also look bottom up. So if I want to know all of the places where I had MPI wait, I can see how much time I spent in MPI wait, and then I can look up the call chains to find all the places where MPI wait was called. And then there's a flat view, so if I'm interested in improving the efficiency of, say, a piece of code that manipulates matrices, then I can look at just how much time did I spend in this matrix code, and what was it like, what's the sum of all of the activity that I spent in here, and attribute that to loop nests and source lines within the loop nests. And then finally, there's some view control options. So there's a flame button where you can point at the top and it says, show me what's important, and it will drill down. And if main is consuming 100% of your time, main or things that main calls, then if there's something that accounts for 50% or more, then it'll open it up and it'll drill down, and it'll keep drilling down. So basically, the flame button says, show me the hot path through my calling context tree. And you can use this flame button at any level. So I can pick a node and then hit the flame button, and it'll show me from that point down. It'll dig into the subtree that's rooted at that node. Then there's also an f of x for computing derived metrics. And then there's also a column view, and what this means is if I've collected metrics for, say, 10 different things, but I want to like narrow my attention to just focus on 2, I can select just the 2 so that I won't have a lot of clutter over here. And then finally, what we see here is this detailed set of contexts. And so I want to point out that the things that are shown in blue here are actual calls. And we also have inline procedures, inline templates, outlined OpenMP loop nests, and loops. And so we get all of this extra detail from our binary analysis, and we overlay that with the dynamic call chains that we've measured. So basically, if there's a lot of inlining that's going on in your program, with our binary analyzer, we'll understand it, and then we can take whatever performance measurements we have and map it back to your source code, even in the presence of full optimization. So the problem that you're probably here to solve is that you've got a code that doesn't scale so well. So what you'd like is, as you go to a large count of processors, you'd like your parallel efficiency to remain at 1 and get the full value of all of them. But typically that doesn't happen, that your efficiency drops off. And what you want to know is, well, what's the difference between my ideal efficiency and where it dropped off? So what we'd like to understand is where the bottlenecks are. We'd like to guide you to where they are, to quantify the magnitude of the bottlenecks, and then diagnose the nature of the problem. Well, as Scott was saying, we don't do the whole thing. So what we can do is we can pinpoint the bottlenecks and show you where they are in the code, quantify the magnitude of the problem, but actually figuring out what the problem is up to you, okay? And so that's something that we can work on with your code tonight in the hands-on session, as Scott suggested. So for instance, let's say you have a parallel climate code. And so it's got land, sea ice, ocean, and atmosphere modules. And all of them are invoking MPI, and all of them have, say, calls to MPI wait. So if I know that I'm spending time in MPI wait, that doesn't help me very much. I actually need to know the context in which the MPI wait was so costly. So I need to know that like the MPI waits in the atmosphere section of my code were not working so well. And so that's a sign that maybe I need to do some refactoring of my code to pay more attention to how I'm managing the communication in this phase. So the performance is dependent upon the layering of the software. And then when we're monitoring, well, there's all sorts of things that could happen. So we may have bottlenecks due to computation, data movement, synchronization, and we want to collect like low volume information and be able to diagnose what's going on. So the good news is that there's a methodology for doing this. So you have some performance expectations for your code. So you either expect that when you run it, that you're going to get linear speed up, that if you run it on twice as many processors, it's going to take half the time. Or if you're doubling the number of processors but also doubling the problem size, that's called weak scaling, then you expect that the larger problem is going to be solved with the same amount of time on double the number of processors. So since you have these expectations for how your code is going to work, then you can put these expectations to work. So you can measure the performance under different conditions. You can measure with a small number of processors and then a large number of processors, or a small number of threads and then a larger number of threads. And then you express your expectations as an equation in a little spreadsheet and say, I expected it to be the same. And then you compute the deviation of your expectations, and the tool will do this for every calling context in the program, and correlate this with the source code, and then you can explore the call tree. So here's an example. So this is like the calling context tree that I explained before. We've associated all of these costs with particular points in your program. So main calls A, calls B, calls C, and then there's some costs that are incurred in C. And so let's say that this subtree represents the solver. And I ran this on, say, 256 cores. Then I run it on a larger problem where I run it on, say, K cores. And I get a different distribution of costs throughout the program. So let's say that I had 400K units of time in the solver when I ran it on a small system. And then when I ran it on the larger system, I had 600K units of time. Well, if we were doing strong scaling, we'd say, well, we actually expect the same amount of effort to be invested in this, so we expect these two numbers to be the same. That's what we would like. So in fact, in this case, there's, say, 200K units of waste in the solver here. So this waste, we can look at this waste as a fraction of the total execution time that I've invested. So what's the total amount of time I spent on Q processors, and what's the fraction of the waste? Like how much is 200K versus the total time that I spent in this tree? So that gives me the fraction of wasted effort. And in fact, so if I multiply by 100, I get the percent wasted effort. But in fact, percent wasted effort is the same as percent scalability loss. So I can directly measure losses in parallel efficiency, and I can attribute to them the code, because I can look at this and then say, starting at the top, show me where the losses are, and it can drill down and it will show me that the losses are in the solver. Okay, seems reasonable. Why don't we look at how to actually put this into practice? So I know that you've heard about the Flash code. Anshu Dubey told me last night that you spent a lot of time talking about the Flash framework that was done at the University of Chicago. So this is a parallel adaptive mesh refinement code, block structured AMR, computing compressible reactive flows, and they have like lots of figures showing helium burning on neutron stars, things like that. So the point is, it's a big, complicated program that's doing complicated things like adaptive mesh refinement. So what we're going to look at is some data from a white dwarf detonation, and this is on one of Argonne's older systems. This particular experiment was run on a Blue Gene P, the predecessor to Mira. And so what we're looking at is the difference between running this on actually 256 cores versus 8K cores. Okay, so let me pull up the user interface. So we're going to look at the source code-oriented view, and we're going to look at the scalability loss with it. So I open up this view. Okay, so what I can do in the source code-oriented view, I have two columns, or I have two sets of columns. I have data for wall clock time measured on 256 cores and wall clock time measured on 8K cores. The reason why there's two columns for each is there's inclusive costs, the time that I spent in this function and everything it called, and exclusive costs, which is just the time that I've spent in a particular function. And so in the navigation pane, I can say, well, Flash, well, it has three phases calls: init Flash, evolve Flash, and finalize Flash. And so when this program was compiled, it was compiled with optimization turned on, but I can just click in the viewer and it's going to show me where the source code is for the function. And I can also see where the function is called. So the little icon over here, it represents a call site. So I can see the driver evolve Flash was called from line 38, and I can see that the function starts on line 40. Okay? Now I can then look inside driver evolve Flash and say, well, what's going on? Well, inside that there's a loop, and then inside the loop there's calls to a bunch of other things. Okay? So this allows me to get this top-down view of the program structure and find out where I'm spending my time. And so at the high level, what we can see is it spends 11.9% on 256 cores. It spends 11.9% in its initialization and 88% of the time in the evolution. Now, if we look at the 8K cores, in fact, what we see is if we compare the top number, we say, how much time did it spend? Well, this is a weak scaling, and so for a weak scaling problem, we expect it to spend exactly the same. So when we scaled it to the larger number of processors, we also scaled the data size. So ideally, the numbers should be the same. Well, so this says 5 times 10 to the 8th, and this says 6.71 times 10 to the 8th. So they're not the same. That means we've got a scaling loss. So also, if I compare the 256 column versus the 8K column, what I can find is instead of spending 11.9% in initialization, I spent 19% in initialization. So let's track down the problem. So what I'm going to do is I'm going to go into this f of x and compute a derived metric. And so I'm going to do exactly what I showed you before with the differencing of trees. So I'll pick the metric that represents the inclusive costs on 8K cores. And so that's represented by $2. So that's it's a spreadsheet-like notation for the particular metric. And I'm going to subtract the time that was spent on the smaller number of processors. And so the difference of these represents the wasted effort. It represents that 200K units of time that I showed previously. Now I'm going to divide that through by the total time that was spent on 8K cores. So there's a different notation for the time at an individual node versus the time at the root. It's like a $sign for the node and then the @ sign for the thing at the root. So now I have something that represents fraction of wasted effort, and I can multiply it by 100 and get percent wasted effort. And as I said before, that's exactly the same thing as percent scalability loss. Okay? And then I can say display this metric as a percent, and then it adds an extra column to my display. So now I have a metric percent scalability loss. So what I can do with this then is say, well, show me where the scalability losses are. So I can point at driver init flash and say, well, show me where the losses are. And it digs down into the call tree, and it says, well, at this place in local tree build, what we can see is this 10% of losses as we're tracking it down, and it's showing me sort of what the largest fraction of that is. It tracks into this point and says, well, half of that appears at this one place in the code. Now, if I go look at what this shows in the code, I notice that it points at this line. Well, what it should be pointing at is a loop nest, but we've recovered the loop nest from looking at the machine code. So instead of showing the node with the loop on it itself, what we're seeing is like one of the first few instructions in the loop. And so what we see here is it says loop over all processors from 0 to nprox -1. And then, so what's going on here is that as part of this adaptive mesh refinement, everybody ends up with some block of computation that they're supposed to be working with. And so as the blocks get subdivided, then they get shifted around between the processors. And what I need to know is who's got the surrounding blocks that are neighbors to mine. And so it goes into this surrounding blocks calculation. So it's using Morton order. It's using a space-filling curve to distribute the blocks among the processors. And then what it does is it's doing an all-to-all communication, but the way it's doing it is it says, well, here's the data that I have. Here are the blocks that I have, and let me send them to my right neighbor. And the data circulates all the way around the ring. And then by the time you're done with circulating it all the way around the ring, you've seen what everybody has, and you've noted who has the stuff that you care about, okay? And so as the data circulates around the ring, we have this loop that goes through all of the processors. And as I scale the number of processors, of course, that's going to involve a loss, okay? So as the number of processors gets bigger, I spend more trips through this loop. So that's going to cause me a scaling loss. Okay, so that's one loss. Well, so this is not just like a one-trick pony. So I showed where under this init flash there was grid init domain. I can also look in grid init and dig into that. Well, I dig in here and I find that this 1.96% of the losses show up with a MPI barrier. Well, right after that, I see do end iproc equals. I look up a little bit. I find that there's some reads. And then there's another loop that says iproc is equal to 0 to npes -1. And so what that says is I have a loop where for each processor I iterate, and then it says if it's my turn, then I open the input file and I read the data. Well, somebody probably put this in a long time ago because they found that when they ran it on a Blue Gene that they crashed the file system having everybody open the file at the same time. So just put in this little loop and then didn't worry about it anymore. Well, now what we see is when we run it on a large number of processors, in fact, this introduces some scaling losses. Small, but yet we can see them with the tool. Okay, so that was the init flash phase. Well, the evolve flash phase actually is very similar. And so if I dig into that, I find out that I'm back in the same place that has to do with the find surrounding blocks calculation, okay? So with taking two measurements, writing a spreadsheet equation, And then clicking the flame button, I can find my scalability losses in the code. Now, when I showed you where the scalability losses are, the tool doesn't tell me what they're for, okay? And it doesn't tell me how to fix them. It just says the losses are here, and then understanding what's going on, like looking around and finding that there's this loop over all processors and that there's this circular communication pattern, that's the part where you come in, okay? You have to think about what your code is doing and what its implications are for performance. So that's how this source code viewer helps you find scalability bottlenecks. Okay, so I showed you the scalability analysis demo, and I showed you how we use this to pinpoint some performance losses. So when we showed this to Anshu Dubey, then what she was able to realize is that, in fact, this general model that they were using this piece of code that they got from NASA that was doing this adaptive meshing. And in fact, they didn't actually have to circulate among all of the processors. In fact, if they looked among the processors in a neighborhood, that was good enough. And so what this shows is the time that was spent in the original calculation. As we increase the number of processors, then the time would go up. So that represented a scaling loss. And then when they replaced it with this custom surrounding blocks calculation, then in fact they were actually able to get flat time. And so they made it so that by replacing this surrounding blocks calculation, so instead of contacting everyone, you'd only look in your local neighborhood, and all of a sudden the application scales. Okay. So that's the source code oriented view. Now, if you end up where you see something in the profile that you don't understand, there's also a time oriented view that can show you how your execution unfolds over time. So what we're doing is we're still doing the same sampling process, and we're still collecting the same call chains. Like when we get an individual sample, we'll collect the call chain saying I was here, and here's the call chain all the way up to main. Now, what we can do to get some insight over time is we can trace call path samples during the execution. So we take a sample at time t1, we take a sample at time t1 plus delta, plus 2 delta, plus 3 delta, and then we have a sequence of samples for an MPI rank or a thread. And then we do this for every MPI rank and every thread in the program, and so we have this sequence of samples. Now, there's this multi-level view. So like up at the top, everybody's in main, but then down below that, maybe there's an initialization and the solve phase, and then down below that, we see the detail of these phases. So let me pull up the same Flash code with this interface. So you get this from the same data. You can collect it and say, I want to do sampling, and then if you say -t, then it will collect the trace data as well. Okay, and so this shows a sea of green. Well, what this is showing me is it's showing me the MPI ranks on the vertical axis, and it's showing me time on the horizontal axis. There's a little crosshair out in the center, and what this shows is the call stack at that point in the execution. So this is for 256 MPI ranks. This is showing me on rank 128, then in fact, there's this call stack that says at this particular time in the execution, we have flash calls, driver evolve, flash calls, hydro, PPM sweep, equation of state, okay? And so this looks pretty uninteresting, but what we're looking at is this top-level view where it says all of the processes throughout time were inside this program Flash. Now, if I move down one level, and it says, well, so for the early part of the execution over here, we were in the initialization phase, and then the rest of it is the evolution phase. The finalization phase is so short you can hardly see it. And then we can move down another level. So this is a top-down analysis, okay? So now I move down one more level. Now it reveals detail within the phases. So I can see, so now I can start picking out time steps, and I can see detail of what's going on where individual time steps. So it's calling this hydro simulation multiple times. And then what I can see is that every few time steps, that there's this little wider phase where I think it's doing remeshing, okay, where there's this purple bar that's a little hard to see from back there. So if I move down further, then I can see detail within the phases. And so there's lots of data here, and then you can zoom in and look at the detail and then see things like, well, there's load imbalance, and so here's something that represents this like a vertical edge that represents a collective communication, and different processes arrive at different times, and so there's waste because they're arriving at different times during the collective communication. And in fact, if we dig down a little further, then we can find out like how this imbalance arises. And so I think what you might be able to see is that There are processes that spend a lot of time waiting, and that's because they do a little bit of this work back in this early phase. And then the processes that arrive late actually had to do a lot of work in this early phase. So what we're seeing is imbalance at a reduction arises because there's imbalance in the earlier computation, okay? Why does that occur? That's up to you, okay? Our tool just shows you that it occurs, okay? Figuring out how you're going to balance the load or whether it's even possible to rebalance the load within the framework of this application, that's a complicated problem. Note that I'm running these viewers on my laptop, okay? So I can view like 8,000 cores worth of data on my laptop. So typically what we do is we collect the data on the big system, then copy it up to your laptop, or you can run the viewers directly off the nodes on the system. So we also have some facilities for monitoring OpenMP. So one of the challenges is that the OpenMP compiler is really doing some violence to your code, and that the implementation level view is not the same as your high-level view. So in fact, for a long time now, we've been working with the OpenMP Standards Committee for what information to put in the runtime system so that a tool could query what was going on in the runtime system and then be able to reassemble this high-level view. So in fact, we do that. We understand that there's a master thread and there's worker threads, and we understand the computation that the worker threads are doing and how it relates to what's going on in the master thread, and we're able to reassemble this high-level view. And so we have this emerging standard where we're actually going to meet in the fall about actually pouring it into the OpenMP standard. So we've had a committee that's part of the OpenMP Standards Committee, and so I'm really hopeful that this support for the tools is going to be there. However, in the meantime, we have an implementation in the LLVM OpenMP runtime, and so this is available with Clang, and there's an installation of this on Mira. So you can use these tools to analyze MPI plus OpenMP programs on the systems here. And what it shows you is this unified view where you don't see this master thread, worker thread. You see call chains that will show you that you're calling OpenMP parallel regions and things like that. And so you'll get to see that. You get to see the source code. There's also a thread level view where you can say graph and show me what each of the threads are doing across an application. And so here's a benchmark, a multi-grid benchmark. And what this shows is that all this gray in here, that represents idle OpenMP threads. And then there's this burst of activity that show that, well, so the master thread initiated all these OpenMP threads, and they were all working together to do build course operator as part of this multi-grid setup. So if you were to look at this, what you would see is that this entire front phase of the computation, the threads aren't working very much. So you're not going to get much benefit from them. So with just this sort of high-level picture, you can understand immediately that you've got some tremendous scalability losses because you're not employing the threads properly. And then you can look into the details of the phases and find out why that happens. And you can do this on larger things. So this is looking at 12 nodes with 48 MPI ranks plus 50 threads per rank per node on a Xeon Phi system at NERSC. And that you can see that there's a lot of idleness. So here I didn't make any attempt to run a larger problem. This is like the same problem I was running on Mira. We were running on this Xeon Phi system. So one other thing that we do is for OpenMP programs, if you find that there's a thread that's sitting idle, that actually doesn't tell you what the problem is. What you need to know is while I'm idle, what is somebody else doing? So we have this technique that we call blame shifting. And so if you're spin waiting and you're idle waiting for work, what we do is we blame that idleness on the piece of serial code that's running. And so for that example that I was showing, this algebraic multigrid, where it's performing this setup phase, all the threads are idle, and what they end up doing is blaming what's running on the master thread that's not being offloaded to any of the other threads. So it's actually very effective. It shows you where the serial code in your program is. So that's the way that the tool is actually taking the measurement data and trying to provide insight into what's going on with your application. So the status of this whole thing is we've gotten a TR approved by the OpenMP Standards Committee. We have prototypes in IBM's implementation of OpenMP and also in the LLVM implementation of OpenMP. And the next steps are like to make this thing real and part of the standard. And so the hope is that by the time the next generation of machine run is rolled out here, based on the Xeon Phi, we would like to have this part of the OpenMP 5 standard. So the schedule for that is there's supposed to be a pre-release of the OpenMP 5 standard at supercomputing, and then a year from now, I think, will be the final OpenMP standard. And so our aim is to have all that in it. So at the end of these slides are some instructions for how to use the tools on the ALCF systems. I have to confess that I haven't proofread these. These worked last year. I have a proposal that's due today. So after this talk, I'm going to turn in my proposal, and then I'll make sure that we have the up-to-date instructions for the hands-on session tonight. So I'd be happy to take a question or two, but we're running a little behind. Yes?
Is there a way to get OpenMP TraceViewer to have a consistent set of colors? I've noticed that between different runs, it seems like the colors change for different parts in the call stack.
So if you're saying that, like, do 2 runs get exactly the same coloring? The answer is no, and the reason is that the algorithm that we use for assigning the color is random. Okay, we found that random assignment of the colors actually works pretty well. Otherwise, it's actually kind of hard. What you want is that colors that are at the same depth in the call stack should be, like, distinguishable. And so we could actually, there's an optimization problem we could solve for color assignment, and we just said random actually works pretty good. So
okay, the problem comes in when you're trying to compare two runs?
If you're trying to compare 2 runs, so actually there is a facility in the TraceViewer where you can actually set colors if you want to compare things. So if you want to take certain things like waiting time at barriers and just set that to red, you can do that.
Right. I've seen that where you can manually assign each. It's kind of tedious. So I was wondering if there's a way to just say.
If you'd like to write a piece of code that does color assignment, consistent color assignment, we would love to take it as a poll on a repository.
I'll shut up now.
Okay. Any other questions?
So do you also give information about what's actually going on through the memory hierarchy and other example, like how well you are utilizing the floating point vector units? And
so one thing that I didn't mention here is that the sampling-based measurement techniques we're using, what I showed you are samples where we're collecting time. But in fact, you can use these samples to collect data with hardware performance counters. So you can collect L1 misses, you can collect L2 misses, you can look at how many instructions you've executed. You can look at the types of instructions. On the Blue Gene systems, it's kind of a challenge to use the hardware performance counters. What we're lobbying for actually is for the next generation systems that they should have an appropriate set of counters so that it's easier to do. But I'd be happy to show you how you can use the counters that are available. Now, in the Blue Gene queue, the L2 cache is actually separated from the processors. And so what you can count is, like, when the counters overflow in the L2 cache, then we can interrupt every thread and say, you know, where are you now? But that's not exactly the same as saying that this thread caused it. Instead, it's like finding there's a set of suspects and a set of perpetrators, okay? And everybody gets, you know, in the same equivalence class. So this is where I was when all the bad cache activity happened, okay? So we can do that, and we can associate with pieces in your program. If you're running a SPIMD program, actually that's pretty good, okay? Be happy to look at that with you this evening.
Okay, let's, we have another question. Hi, let's say I have a program and there's a function f, and I'm passing a parameter into f, and which would vary the load balance of that particular function. Now it's the same execution, in the same execution in the program, is it possible to separate out the profiles for different executions of that function f?
So if the different functions if f is called in different contexts, then we can see that. If there's a different parameter that's passed to it, where sometimes you pass 3 and sometimes you pass 4, we can't see that today. So one way that we could do that is there's a system at Livermore called Caliper where you can put in annotations into your program. And then what we'd like to be able to do is actually to take this data and say, well, let's slice what we're showing you with respect to when you pass 3 to F or when you pass 4 to F. But if what you want to do today is get this answer, well, when you pass 4 to F, you could just create a different context and say, if it's 4, then call F here, and if it's 3, call F here, and you can get exactly the data you're looking for. Okay, requires a little work on your side, but
And does it interface with the PAPI, the PAPI interface?
so we don't typically wrap the PMPI interface. We don't typically wrap MPI functions. We can, but we don't typically. We use the PAPI interface, the
Yeah, that's the
PAPI,
one.
to measure performance counters.
Yeah. Okay. Thanks.